students, good afternoon. In last class, we derived some expressions. Those are depends upon the lens. As well as we study about the different image formation due to the concave lens as well as convex lens. Then in last class, we derived the expression that is a relation between N, U, V, R. As well as we derived the another one expression that is a lens maker's formula. This here, according to the lens maker's formula, that 1 by F is equal to 1 by V minus 1 by U. So, but that formula is related for one lens. But when the number of lenses are in contact, then we derive the expression for the combination of a lens. Then what is the equivalent focal length when the number of lenses are in contact? So what is the equivalent focal length? To derive that expression, derive equivalent focal length, derive the equivalent focal length, when derive equivalent focal length when two convex lens are in contact. So here, derive equivalent focal length when two convex lenses are in contact. When there is only one lens, then the focal length depends upon the object distance and image distance. Or the focal length of each material is a constant, and that focal length can be found out by using the image distance and object distance. That related formula is 1 by F is equal to 1 by V minus 1 by U. We apply the Cartesian sign convention. But in this derivation, if the number of convex lenses are combined to each other, what is its equivalent focal length? To derive this expression, we consider the two convex lenses. So, to derive this expression, we consider the two convex lenses. This derivation is also related for 3 mass or 5 mass. This formula is related for the numericals. Then say how to derive this expression. Here, consider the two convex lenses. We know that convex lens is a convergent lens and concave lens is a divergent lens. Due to the convex lens, we have got the image that is a convergent. Means the focal length of a convex lens is a plus, and the focal length of a concave lens, due to the divergent rays, there is a principal focus is found out, and that is known as the focal length of that concave lens, and that is a negative. So in this type, the focal length of a convex lens is a positive, and the focal length of a concave lens is a negative. But here we consider the convex lens. Then here, when the two thin lenses are those whose refraction is a very small. Means there is a refraction is a negligible. Means the incident ray and emergent ray both are parallel to each other. That is known as the thin lenses. Then here, if we consider the two thin lenses, those are in contact to each other. Suppose this is the first lens, convex lens. Consider the another one lens which is in contact with the first lens. Then here, consider the two convex lenses. The focal length of both the lenses is different. If the focal length of first lens is a F1, focal length of first lens is a F1, and focal length of second lens is F2. So we consider the two convex lenses whose focal length is different. When those are combined to each other, or those are in combination with each other. This here, it draw a principal axis which is passing from the optic center, both the optic center. Then, suppose this is optic center first, optic center second. If we consider the point object, if we consider a point object on the principal axis, that is a O being a point object, which is on the principal axis, which is a place on the principal axis, then we know that this object is a luminous object, and from this object, number of light rays are propagated. Suppose the first light ray, which is propagated on the principal axis without undeviated, according to the laws of refraction, when the I is 0, R is also 0. Then consider the another one light, which is an incident on the lens. Consider the another one ray of light, which is an incident on the first lens, and it is a refracted, and which is an incident on the second lens. And again, this ray of light is a refracted, and we have got the image on the principal axis. So here, when we consider the two thin lenses, those thin lenses are in contact to each other. Both the lenses are convex lenses, and the focal length of a first lens is a f1, focal length of a second lens is a f2. If the object is situated on the principal axis, and this is a point object, from the point object, number of light rays are propagated. If we consider sum of the light rays to draw the image formation, then see how the image is formed due to the thin lenses. So here, first ray of light is propagated from the principal axis or both the optic centers, and this ray of light is propagated straight line because incident angle is 0, so the refracted angle is also 0. If we consider the another one ray of light, which is an incident on the first lens, then this ray of light is propagated from rarer to denser medium, and it again refracted in the denser medium in the another one lens, and again the ray of light is propagated from the denser to rarer medium. So in this type of, we have got the final image. So here, this is a final image, and this image is due to the both the lenses. This image is formed due to the both the lenses. So here, this distance is known as the image distance, and image distance is denoted by the letter V. And this is the object distance, and object distance is denoted by the letter U. Then here, when we simplify this, in the last class we also derived the lens formula by using the two spherical surface. So in the same time, we derive this expression also by using the two lenses, two separate lenses. Means in this also, there are two refractions are there, and due to the two refraction, the final image is formed. Means first, the refraction is takes place due to the first lens, and again the refraction is takes place by using the second lens, and we have got the final image. But to find out the final image, there are two stages are there. To find out the final image, there are two stages are there. So here, express that formula or explain that formula by using the two stages. And we know that these are the convex lens, and due to the convex lens, we have got the real image. Due to the convex lens, we have got the real image. Then see how to express this. Means first case. In first case, the refraction is takes place due to the one lens. Suppose this is a lens 1 and this is a lens 2. Consider the refraction in the two lenses. The refraction is takes place by using the two stages. First stage is refraction due to the first lens. So refraction due to first lens. First lens. So here, when the refraction is takes place due to the first lens, consider the first lens. Consider the first lens. So this is a convex lens. Draw a principal axis. This is the optic center. If the point object is situated, The first ray of light is propagated without attenuated. Second ray of light is an incident. That is a OP. Suppose this is a ray of light OP. Suppose OP is the incident on the first lens. So this ray of light is propagated from rarer medium to the denser medium. Means here the object is also real, and due to this lens, the image is formed. That image is also real. So here object is a real. At the same time, the image is also real. So after diffraction, we have got the image. Means here the ray of light is an incident on the lens, and the ray of light is a refracted, and we have got the image. But this image is not a final image. This image is not a final image. This image is found due to the one lens. This image is found out due to the one lens. So here, this image is not a final image. So we give the name here I1. Give the aromas. This here, this I1 is an image. Means from O to I1. This distance is known as the image distance. But this is not an image here, final image. So we consider here V1. Image distance due to the first lens is a V1. And here the object is same, and that is known as a U. Explain the figure. We consider the one lens, and the object is situated on the principal axis. From the object, number of light rays are propagated. If the first ray of light is propagated undeviated, second ray of a light is an incident on the lens, and it is refracted, and we have got the image. But this image is not a final image. But this image is formed due to the first lens, and this image is real. At the same time, the object is also real. Then apply the lens formula. We know that in the last class we derived the expression for the lens formula, and the lens formula is 1 by f is equal to 1 divided by v minus 1 divided by u. So for this figure we apply the lens formula. Then substitute the values. So in this there are two lenses are there. So when there are two lenses, the focal length of the first lens is a f1, and the focal length of the second lens is a f2. Then the focal length of the first lens is a f1. So give the name here 1 divided by f1 is equal to, what is the image distance here? Image distance is due to the first lens is a v1. The image distance due to the first lens is a v1. This here 1 divided by v1. But if v1 is, the question is arises that v1 is a positive or negative. Then according to the partition sign, OP with a ray of light which is an incident, and the direction of an incident ray is in this direction. And we measure the image distance is also in the same direction. That is the incident ray and image distance both are in the same direction. So we consider V1 is a positive. We consider V1 is a positive. Then here what about the object? Minus. There is an object distance minus u. Means here we apply the partition sign already. We observe that is a correct or not correct. Minus u. See here, minus u means object is situated in the opposite distance of the incident ray. So see here, incident ray is in this direction. We measure the object distance in the opposite direction. Means u is a minus. So it is a correct. So this formula is applicable for the first lens. So this is the equation number 1. This equation is known as equation number 1. So this lens formula is applicable for only first lens. But the image formation takes place due to the two refraction. Then here, what about the second lens? How the image is formed due to the second lens? Refraction due to the second lens. This is the first case. Second case, refraction due to the second lens. Refraction due to second lens. Refraction due to the second lens. Then consider second lens. So when we consider second lens, see here, consider the second lens. When we consider the second lens, we consider this portion only. We consider this portion only. Means when the refraction is a takes place due to the second lens, that time the object is a not worked. The real object is not there. We consider only half of the portion, or we consider the second part of that figure is there. So we consider second lens. So here, this is a second lens whose focal length is a f2 and the lens is a L2. A principal axis. This here, when we consider half of the part, we have got already the image I1 due to the first lens. So consider the image I1. So when we consider the image I1 due to the first lens and the distance of the image is a V1. So in the second case, the image which is find out due to the first lens is a work as an object. The image which is find out due to the first lens is a work as an object. But this is not a real object. This object is known as a virtual object. So this object is a virtual object because this is an image due to the first lens. So here, this is a, so the ray of light is an incident from the image on the second lens. It is a divergence and the ray of light again come back. When the ray of light is a divergence, and again come back in the same medium, and we have got the image. And that image is known as the final image I. So this distance is a V1. And the final, after diffraction, the image is a find out and that image is a I. So this is the final image. So here, in this type, we have got the final image. So when we consider the second lens, that time there is a object is considered as an image due to the first lens, and this image is a work as a object for the second lens. So the ray of light is an incident from the image, and again there is a divergence and come back in the same medium, and we have got the final image. So here, in this case, the object is a virtual, but the image is real. So in the second case, the object is a virtual and the image is a real. Then again apply the formula, lens formula for this figure. And we know that the formula is 1 divided by f is equal to 1 divided by t minus 1 divided by u. We use here the lens formula. When we use the lens formula, substitute the values for this figure. This here, 1 by f, f means focal length, and the focal length for the second lens is a f2. So substitute the value. 1 divided by f2 is equal to 1 divided by v, that is the image distance. So here this is the image distance, 1 divided by v. But the object is at a distance v1, and that is a object is a virtual. So we consider here minus 1 divided by v1. So this is the equation 1 and this is the equation 2. This equation is a find out due to the second lens, and this equation is find out due to the first lens. Then add both the equations because here we want to find out the equivalent focal length. So add both the equations. When we add in both the equations, when we add both the equation, that is 1 and 2. Add equation 1 and 2. When we add both the equation 1 is 1 divided by f1 is equal to, adding both the equations means the first equation is 1 divided by f1. Another equation 1 divided by f2 is equal to 1 divided by v1 minus 1 divided by u plus 1 divided by v minus 1 divided by v1. So when we add both the equations, we have got 1 by f1 plus 1 by f2 is equal to 1 by v1 minus 1 by u plus 1 by v minus 1 by v1. So cancel the same values. When we cancel same the values, that is a 1 by v1 minus 1 by v1. we got the new equation, that is a 1 by f1 plus 1 divided by f2 is equal to 1 divided by v minus 1 divided by u. So we got the new equation 1 by f1 plus 1 by f2 is equal to 1 by v minus 1 by u. Then according to the Lenz formula, 1 by v minus 1 by u is equal to 1 by f. So substitute that value. 1 by v minus 1 by u is equal to 1 by f. This is the Lenz formula. So substitute the value in this equation. So this equation becomes 1 by f1 plus 1 by f2 is equal to 1 by f. So here, in this type, when the number of lenses are connected to each other, that time reciprocal of this is an equivalent focal length. Means when the number of lenses are in combination to each other, its equivalent focal length is reciprocal of the focal length. So in this type, when the two lenses are in contact, the first focal length is a f1, second focal length is a f2. The reciprocal of this is an equivalent focal length. Means 1 by f1 plus 1 by f2 is equal to 1 by f. Otherwise, if there are number of lenses are in combination to each other with a different focal length, then we can find out the equivalent focal length by using this formula, that is a 1 by f1 plus 1 by f2 plus so on plus 1 divided by fn is equal to 1 by f. So this is a formula which is related when the number of convex lens are connected to each other. Or with the concave lens also, we use the same formula but apply the Cartesian sign, because the focal length of a concave lens is a minus. For example, one lens is combined with another concave lens. That time we have got the formula 1 by f1 minus 1 by f2, because the focal length of a concave lens is a minus. Therefore, 1 by f1 minus 1 by f2 is equal to 1 by f. Means we can find out the equivalent focal length when the number of lenses are combined to each other. So this is a very important formula, or this is a very important derivation for you. This is a very important formula to solve the NEET questions or to solve the numericals, famous numericals. This here, there is another one important form is there. In the last class, we discussed the power. And we know that power is the reciprocal of a focal length. Power is a reciprocal of a focal length. Means 1 by f is equal to p. So if we want to find out the power, means this is a p1 plus p2 plus so on, pn is equal to p. So this is a related formula to find out the power. So in this type we derive the expression for the focal length when the number of lenses are connected or combined to each other, and we find out the equivalent focal length by using this formula. So when the number of thin lenses are combined to each other, the related formula is 1 by f is equal to 1 by f1 plus 1 by f2. That f1 and f2 sign convention is depend upon the lens. If the concave lens is there, we take the 1 by minus f. So when the two thin lenses are in contact, we use the formula 1 by f is equal to 1 by f1 plus 1 by f2. And its form in the power is P is equal to P1 plus P2. By using this formula, we can find out directly power. But here, when these two lenses are in contact to each other, that time we use this formula. But when two thin lenses are separated from each other, means there is a small distance in between the two lenses. So there is no need of a derivation, there is need of a formula directly. So when the two lenses are in contact to each other, but those are separated by each other with a small distance d. That time we use the formula. This formula is related for the numericals, otherwise other CET or NEET questions. So when the two lenses are separated by each other with a distance d, that time its equivalent focal length is, with the focal length of first one is a f1, focal length of the second one is a f2. Then its equivalent focal length is 1 by f is equal to, it is an equivalent focal length. 1 by f is equal to 1 divided by f1 plus 1 divided by f2 minus d divided by f1 f2. So this formula is related for the numericals. When the two thin lenses are separated by each other, means both the lenses are convex lens. That time we take f1 and f2 both are positive. But if the another one lens is a concave, if one lens is a convex, another lens is a concave, f1, f2, that time its equivalent focal length is 1 by f is equal to 1 by f1, that is a convex lens focal length is a positive, minus 1 divided by f2. So here, this is the focal length for the concave lens. This minus minus plus d divided by f1 f2. So in this type, we use the Cartesian sign. Or remember this formula, and depending upon the lens, we use the Cartesian sign. So this formula is related when the two thin lenses are in contact, but those are separated with a distance d. This here, how the lens is a work as a convergent and divergent. Convergent and divergent depending upon the surrounding medium. Means when the lens is situated in the other medium, when the lens is placed in the other medium. For example, how the lens, convex lens is used as a concave lens, or concave lens is a work as a convex lens. Means when the convex lens is a work as a convergent, or when the convex lens is a work as a divergent. So this is an important point for your other exams, NEET exam, otherwise CET exam. So here, when there are two refractive index are there, refractive index for the lens and the refractive index for the surrounding medium. If we consider the N2 be the refractive index, N2 be the refractive index for the lens, and the surrounding medium is a N1. N2 refractive index for the lens, refractive index for lens, and N1 refractive index for surrounding medium. Surrounding medium. So consider lens. Consider any lens. Suppose if we consider the convex lens. Convex lens is a convergent lens. Consider a convex lens. So if we take convex lens, this is a biconvex lens. So draw a figure when the ray of light is an incident in the same medium. N1 is equal to N2. So this is a lens whose refractive index is a N2. And this lens is a placed in a surrounding medium whose refractive index is a N1. But here the question is that draw a ray diagram when both the refractive index are same, means N1 is equal to N2. So here what happened there? When the ray of light is enter, if in the air medium, if the ray of light is propagated in the straight line direction, in the air medium, the ray of light is propagated in the straight line direction. So here, this medium is known as a N1. And when this ray of light is enter in the glass, when the ray of light is enter in the glass, then how the ray is diverted here? The ray of light is a convergent, or the ray of light is a divergent, or the ray of light is propagated in the same medium. We know that the ray of light is propagated in the same direction in the same medium. Means if the refractive index is the same, the ray of light is propagated in the same medium. And we know that the refraction is takes place when the ray of light is propagated from one medium to the other medium. Or when the refractive index is changes, means the direction of the ray of light is also changes. But if the refractive index is not does not changes, means the ray of light is propagated in the same direction. Then here N1 in this ray of light is propagated, but this glass is also made with the refractive index is the same with respect to the another. Then that time, if this is a water glass and this is also water, means the medium is the same, and due to the medium is same, the ray of light is propagated in the straight line direction. Means where the this medium, this glass as well as the surrounding medium work as a homogeneous medium. Means in this type of when the remember when the ray of light is enter in N1 is equal to N2. With respect to the surrounding medium, refractive index is the same. With the refractive index of a glass is also same. That time, the ray of light is propagated in the straight line direction without undeviated. So remember this ray diagram. Without undeviated. This is the first figure. And N1 is equal to N2. Then see the second figure. In the second figure, when N2 is greater than N1. N2 is greater than N1. Draw the ray diagram. When N2 is greater than N1, means consider a convex lens. In this convex lens, this refractive index of the lens is N2, refractive index is N1, and when the ray of light is means N2 is greater than N1, means this medium becomes as a rarer. This medium becomes as a denser. So the ray of light is propagated from rarer medium to the denser medium. And we know that when the ray of light is propagated from rarer to denser, it converges. This is a converges. Then see how the ray of light is a converges. When the ray of light is propagated parallel to principal axis. So this is a air medium and this is a denser medium. So when the ray of light is propagated from air medium to the denser medium, it is a converges. Converges means it bended towards the normal. So it is a converges at a principal focus. So this is a ray diagram. When the ray of light is propagated from the when N2 is greater than N1 and the ray is propagated from the rarer medium to the denser medium. So this is the ray diagram. See the next one. When N1 is greater than N2. When N1 is greater than N2. Means when the lens is placed in that medium whose refractive index is more as compared to the glass, as compared to the lens. Then what happened there? This lens is a convergent. This lens is a plane lens. Means there is a no refraction is takes place when N1 is equal to N2. But N1 is less than N2, that time this lens is a work as a convergent. But when N1 is greater than N2, so here if we take the lens whose refractive index is a N2, draw a principal axis. When the ray is propagated from air medium, so the ray of light is propagated, whose refractive index is a N1. But here what happened? Refractive index of this medium is greater than the refractive index for the lens. Refractive index for the this medium is greater than the refractive index for the lens. That time the ray of light is bent away from the normal. We know that when the ray of light is propagated from rarer to denser, it bends towards the normal. This ray of light is propagated from rarer to denser, it bends towards the normal. But when the ray of light is propagated from denser to rarer, means it bend away from the normal. So this time the ray of light is bent away. So here convex lens is a work as a concave lens. Remember that concave lens, the convex lens is a work as a concave lens when it is placed in a denser medium. When it is placed in a denser medium. So we know that when a small air bubble inside the water, when the small air bubble inside the water. Air bubble means the refractive index of air is less as compared to the water. That time that bubble is work as a concave. Suppose this is the air bubble which is a place in the water, which is a place in the water. Means this is the air bubble. So air bubble means here N2 is less than N1. So that time the refractive index for the surrounding is a more. So there is a pressure is takes place and this is a work as a concave. So that time it looks like a concave. So in this type of when the lens is a placed in a surrounding medium whose refractive index is a more, that time that lens is a work as a concave lens. So remember these points. So the lens is a work as a concave lens. When the ray of light is incident on it, it is a divergence. So here at the same time, these related figures are for the concave lens. These figures are related for the convex lens. Then draw the figure with related to the concave lens. Again, we take the two mediums. Due to the concave lens. The first figure is due to the concave lens, N1 is equal to N2. When the concave lens is placed with respect to the surrounding in the same medium. So here this is a concave lens. Concave lens is a divergent lens. Draw a principal axis. So this N2 refractive index which is placed in the surrounding medium N1. That time when the ray of light is incident on this is a work as a plane surface because when the ray of light is enter from the refractive index state and it is an incident on the same refractive index, that time the ray of light is propagated and deviated. Means there is a no refraction is takes place and this is a work as a plane. This is a work as a plane surface. So in this type, the concave lens, when the ray of light is enter from the same medium or when the concave lens is placed in the same medium, that time there is a no refraction is takes place and the ray of light is propagated without undeviated. So this is the first. Second, when N1 is less than N2, means the ray of light is propagated from rarer medium to the denser medium. So here, this is a concave lens. When N2, refractive index for the lens is a N2 and the surrounding medium is a N1. When the concave lens is placed in a rarer medium, draw a principal axis. When the ray of light is enter on this is a concave lens. Concave means divergent lens. Divergent means when the incident ray is when the ray of light is incident on the concave lens, it will move away from the normal, or it is a divergent means move away from the principal axis. So that time the ray of light is propagated away from this. And the same time, this is a work as an actual. This is a concave lens. This is a ray diagram. So when the concave lens is placed in a surrounding medium whose refractive index is less, that time it will work as a concave lens. But when it is placed with the surrounding medium is less. Third figure, when N1 is greater than N2. N1 is greater than N2. So that time, consider the concave lens whose refractive index is N2, which is placed in the surrounding medium, whose refractive index is N1. But here the refractive index of the surrounding medium is greater than the refractive index of a glass. So that time, when the ray of light is incident on it, but when the ray of light is entered from rarer to denser, it bend away from the normal. But here, the ray of light is entered from denser to the rarer medium, means it bend towards the principal axis. So in this type, it work as a convergent. It work as a convergent. So when the concave lens is placed with the surrounding medium is a less or less refractive lens, that time this work as a convex lens. That time this work as a convex lens. So in this type, these are the main three figures to draw the ray diagrams or to solve the numericals. When the surrounding medium is the same, this is a work as a the ray of light is a passes without undeviated. But when the surrounding medium is a rarer, where this is a divergent ray, the ray of light is a bent away from the principal axis. Or when the ray of light is a incident on it, with the surrounding medium is a more, that time it is a directed towards the principal axis, and this is a work as a convex lens. So in this type, these are the uses or these are the main diagrams. Those are related for the ray diagram. Then the next part of the lens is a magnification. Magnification means what type of image is find out. That image is a magnified, means that image is a erect, or that image is magnified, or the image is a diminished. To explain that figure, we take the ratio of the height of image to the height of the object, and that ratio is known as a magnification. So here, what is the meaning of magnification, and what is the related formula for the magnification? Magnification. So magnification is a defined as magnification. Magnification is defined as magnification is a defined as it is the ratio of it is the ratio of it is the ratio of height of the image height of the image to the height of object to the height of object height of object height of the image to the height of the object is known as a magnification. Then here, magnification is equal to height of the image divided by height of the object. So height of the image is in the downward direction. That time, according to the Cartesian sign, we take here minus. When the object is in the upward direction, we can take here plus. Means when the image is formed due to the convex lens, that time we have got the image inverted and real image. That time we use the formula minus hi by h2. So what is the relation or what type of magnification? Means when the magnification is a 1, when the magnification is equal to 1, that time the height of image and height of object both are same. Means we have got the same image due to the lens. So that is known as a magnification. Then here how we derive the expression for the magnification, or what is the related formula for the magnification. If we draw the ray diagram, by using the convex lens, if the object is situated on the lens, if AB be the extended object and the ray of light is an incident on this and it is a convergence, and another one ray of light is a propagated from the optic center. So this AB is the height of a object. This A dash B dash be the height of the image. So here AB be the height of object. So this is the height above the principal axis is considered to be positive. Height below the principal axis are considered to be negative. Means here HO, that is the HO is positive. HI, that is below the principal axis, is considered to be negative. That is magnification is equal to minus hi divided by ho is known as a magnification. Then what is the relation in between this v by u as well as the height of image and the height of object is derived by using this figure. So to derive this ratio, consider the similar triangles. Consider the similar triangles ABM. Consider similar triangles ABM, ABM and A dash B dash M, A dash B dash M. So when we consider the similar triangles, so here height of image is A dash B dash divided by AD is equal to another one side is NA divided by NA dash, NA divided by NA dash, NA divided by NA dash. Otherwise, consider this is the O, optic center. Substitute the values. A dash B dash is known as the height of image minus hi. AB is considered to be HO is equal to OA. OA is considered to be object distance, that is a U. OA is equal to U divided by OA dash is considered to be image distance. Here object distance is in a opposite direction, so we consider here minus. And OA dash is considered to be image distance, and the direction of the incident ray and the image distance both are same, so we consider here plus. Then minus hi by ho is known as a magnification. So magnification is equal to minus hi by ho. So substitute the value in this equation, means m is equal to minus u divided minus OA is a similar side, that is a OA dash divided by OA. Means we have got there image distance divided by u. When we consider the similar sides, this OA dash, A dash, B dash divided by AB is equal to OA dash divided by OA. OA dash is known as a V, OA is known as a U. Where U is in opposite direction, so we consider minus. So here minus V by U, and this is known as a magnification. Means there are two formulas are there. Magnification is equal to minus hi by ho. Otherwise, magnification is equal to minus V divided by U. We use both the formulas. So here minus hi by o is equal to minus V by U. Both are becomes as a minus minus plus. That is a hi by ho is equal to V by U. Hi by ho is equal to V by U. And m is equal to hi by ho, otherwise v divided by o. So this is a related formula for the magnification. So this formula, by using this formula, we define how the magnification is. Means if the image is a diminished or if the image is a magnified. If the height of an image is more than the height of an object, if height of an image is more than the height of object, that time we say that the image is a magnified. But when the height of an image is less than the height of an object, that time we say that the image is a diminished. Means by using this, or both the values, this height of image is a minus, that time we say that the image is a inverted. Or if the both are in the upward direction, both are positive, means we say that the image is a erect. So in this type, we study about the image formation due to the convex lens, as well as we derive the expression for the magnification. So in this type, we derive as well as we find out the value of a magnification. Otherwise, this is to find out the different formulas. To find out the different formulas means when we want to find out some values, image distance, object distance, or there is to find out the magnification by using the focal length. That time some other shortcut formulas are there, and we find out those shortcut formulas. And those shortcut formulas are related for the numerical study, not for the theory exams. So here, how to find out The formulas, those are related for the object distance and the focal length. So here, according to the lens formula, 1 by f is equal to 1 by v minus 1 divided by u. We find out the different formulas. Those are the different shortcut formulas. So 1 by f is equal to 1 by v minus 1 by u. So when the focal length is related with the magnification, so that time multiply this equation with the v. Multiply with the v. When we multiply both the sides with v by f is equal to v by v minus v by u. So here, v by f is equal to v by v minus v by u. So v by f is equal to v by v is equal to 1 minus v divided by u. So if we take this side, v by u is equal to 1 minus v by u, and when this goes to this side, 1 minus v by f. So we know that v by u is equal to magnification. So m is equal to f minus v divided by f. So this is another one shortcut formula. When the focal length is given, image distance is given, we can find out the magnification. Otherwise, when the magnification is given, we can find out the focal length as well as the image distance. So this is another one formula which is related to the find out the magnification. Otherwise, this is when we multiply with the value of a v. If we multiply with the value of a u, when we multiply with value of a u, multiplying with u. So this is a shortcut formula. Multiplying both the side with u, that is a u by f is equal to u by v minus u divided by u. So this value is a 1. Therefore, u by f is equal to u by v minus 1. Therefore, u by v is equal to u by f plus 1. U by v is equal to u by f plus 1. Cross multiply this value. U by v is equal to u plus f divided by f. Reverse this equation. P by u is equal to u plus f. Sorry, u by v. P by u is equal to f divided by u plus f. So what is the meaning of v by u here? That is a magnification. So magnification is equal to f divided by u plus f. Means if the image distance is not given, object distance is given, we can find out the magnification by using this shortcut formula. That is, the magnification is equal to f divided by u plus f. Apply the Cartesian sign. If the concave lens is there, f is a minus. If the convex lens is there, f is a plus. So in this type, we derive some important formulas as well as important derivation in this chapter, lens. So in the refraction, there are different parts are there. Refraction through the plane surface, refraction through the curved surface, refraction through the lens, and in the next class, we study about the refraction through the prism. Thank you.